Welcome to our last week of lectures. This week we're going to be showing you applications of what you've learned and summarizing some of what you've learned this semester. It's great to see you all again this week after the break. Some brief announcements. Your last homework, that's worth hearing again. Your last homework is due this week. Your project, project 3 is due on Friday. So I hope you've been making good progress on that. Please work hard on that this week. There will be lab this week. We will do the final lab. And then we will have announcements later about our schedule over our week. We'll have resources for you to help you prepare for the final exam. Okay, so what we're doing this week. Today, I wanted to kind of walk you through what we've learned so far this semester in Data 8. I think it's remarkable how much we've been able to go through, and I wanted to give you a feeling or a sense of that. On Wednesday, we'll have a special guest lecture on algorithmic bias and the potential for bias in machine learning and data science and our use of algorithms for making automated decisions. And then on Friday, we'll have our final lecture. Okay, so what have you seen in this class so far? We've studied data science, and I hope that this course has helped make the case for why data science is a exciting new field. First, we've got unprecedented access to data sets, to more data than we ever had before, which enables us to make new discoveries and make more informed decisions. Another thing that's happening is that we're discovering that computation can be a very powerful friend in analyzing data. It can help us with visualization, with making predictions, with statistical inference. And I hope you've seen that in this class. One of the themes of this class is that instead of burying you in math, we've tried to use computation as our core tool to do a lot of data analysis. One of the things that I find exciting about data science is that in today's world where we're so divided and we have such a range of opinions, one thing we can do is we can look to the evidence. And data science gives us some tools to analyze data, identify the evidence, and measure what's happening in the world. And maybe a last comment is that data and computation are everywhere, and my expectation is they're going to be very important to your life and to society throughout your lifetime. And so understanding what's going on here and how to interpret it and what its strengths and limitations are and what effects it might have on you, I think it's important that you be informed citizens so that you can make good choices about what world you want to live in. So that's why I'm excited in data science, but let me also mention some of the limitations that hopefully you've seen, and I think it's good to keep in mind. Evidence and measurements and data, very powerful for making good decisions, but they're not enough by themselves. They can't tell us what decision to make. They can potentially give us some idea of what the impact or effects of different decisions might be. So data science is a powerful tool, but for instance, it doesn't tell us what our values should be. It's not everything. It can help give you quantitative analysis, but we also need the qualitative too. Okay, so let's walk you through some of the themes we've been teaching you in this class about how to analyze data. Got a data set, you want to understand something going on about the world. The approach that we've tried to show you by example is a three-step approach. So start with some question from some domain that we care about, and hopefully some data that's relevant to that domain. So we start with some data set. And then we typically are going to need to understand that data set. We might need to make some assumptions or understand how the data was gathered or what the sampling procedures were. What methods were used in collecting the data and understand what their effect might be. You also often will need to start from some question, maybe that's inspired by that application domain or by something you find interesting about the world. And then we can jump in with the techniques you've learned here. Our advice is that you start with exploratory data analysis. You start by visualizing the data, understanding what's there, using that to form some hypotheses or look for possible trends or patterns. Use that to help you formulate or refine the question you're trying to ask. And then you can do quantitative analysis to try to answer the question. So for instance, maybe that's a hypothesis test. Maybe that's some kind of linear regression model. Maybe you're doing some statistical estimation or inference. Finally, once you've done that and you've gotten the conclusion of your quantitative analysis, don't stop there. One message we want you to take away is that it's not enough to know how to do the technical analysis. Maybe the most important part then is to understand how to interpret what that means, to understand what you found and to be able to communicate it to others in a language that those folks are going to be able to understand. So without being deeply immersed in jargon that isn't going to mean anything to them. So this is really critical because if you know how to do the technical analysis, but you don't know how to communicate your findings, then you're probably going to be a lot less effective. In some classes, you might find that the focus is entirely on the quantitative analysis. So here's a pitfall. The pitfall is that you can get so focused on the math and the stats and the computer programs and the specific techniques for doing the quantitative analysis that it's easy to forget to do all the rest, to understand the question, understand the data, understand the data set, figure out how to communicate your results. So we hope that you will have learned some ideas from this class that will help you be well-rounded and be able to address all of these points. And last, the unique theme of this class is that we've been teaching you how to do the exploratory analysis and the quantitative analysis using computation. So you don't need to know a lot of calculus or math. And our hope is that this makes data science more accessible to a much broader range of folks, so that if your real interest is in the biology of marine mammals or urban decay or the formation of mountains, that you can then use these techniques to go analyze the domain that you actually care about without having to have a degree in statistics or a degree in computer science. Okay, so if we kind of look back on what you've learned in this class, we taught you how to manipulate data in tables and how to do a little bit of Python programming. I hope you'll find that useful. We've taught you about statistical inference and estimation, how to answer questions about how the world works or what is the truth about the world around us based on limited data that we've observed. We've looked at how to measure and understand the amount of uncertainty in our conclusions. For instance, when we draw an estimate, we've learned how to quantify how much uncertainty there is in our estimate, how much variation there might be due to sampling. And we've learned how to make predictions about the future, and you're getting to practice that in your project 3, where you're looking at using classification to make predictions about, well, could be anything. What kind of movie is this? What what album might you enjoy next? And then finally, hopefully we've given you a little bit of practice in explaining your findings to the public. So I thought maybe I could walk us through together what we've learned by looking at some examples. And this is fun for me because I get here to one of the motivations for why I love teaching this course, why I find it so inspiring, which is that I think to be good scientists, good citizens of the world, it's important for us to be literate about how to understand scientific findings. When you read in the newspaper says, a study showed that such and such chocolate was good for your health, or that sleeping longer is linked to living longer, or any number of things. Where does that come from? I want to show you that from this class, you have learned a lot of tools that could help you get surprisingly far in understanding what's going on in the actual study. So let's just kind of do a before and after comparison. Before data 8, you might have read a newspaper article. For instance, we talked in lecture 2 about chocolate and heart disease, and these newspaper articles that said, chocolate's good for your heart. A study found that chocolate reduces heart attacks. Okay. After the end of the second lecture, hopefully we equipped you with enough language that you could then start to dive into that a little bit more. Start to look at some of the numbers. For instance, see that this study reported, the newspaper article is quoting the study as saying that those who ate a lot of chocolate, 12% got heart disease, and those who didn't eat a lot of chocolate, 17% did. And so now you're equipped to understand that in the language of, okay, there's an association here. Now, what does that mean about causation? Can we conclude that eating chocolate will reduce your risk of a heart attack? Well, now by the end of the semester, you actually know a lot more. And I thought it was interesting to pull up the scientific paper that inspired these newspaper articles. This is the actual study that the newspaper articles were trying to summarize and report on. And you can see that here on the right-hand side. So if I zoom into this, if I zoom into one part of the paper, the results section of the paper, it's kind of interesting. If you were to take a look at this paper, you might be surprised by how much you could understand about what's going on in this paper. You probably won't understand everything. You might not be an expert in public health and cardiovascular disease, and so there might be aspects that are challenging to follow. But it's surprisingly often you can get a semi-decent sense of what's going on, enough to start to form your own opinions. Okay, so here is the results paragraph from this paper. Let me highlight one piece of that. All right, you see this multivariate adjusted HR for CHD 0.88. What's going on there? Let me unpack that for you. Multivariate adjusted, well, okay. Okay, there's some statistics that you don't know that you have yet to learn. So there's more to learn after data 8. HR, that's short for hazard ratio. And actually you've seen this in project 2. Another word for that is relative risk. So this paper is saying the relative risk is 0.88. CHD, what's that? That's coronary heart disease. Okay, so loosely speaking, relative risk of heart attacks was 0.88. And so that's an estimate. They're doing statistical estimation. And you can also see here they report a 95% CI, 95% confidence interval for that relative risk. That confidence interval is from 0.77 to 1.01. All right, so someone want to interpret this for me? It's a lot of words and a lot of numbers. What does it mean? What does 0.88 mean in this context? Want to interpret for me a 0.88? Go ahead and type in the chat. Maybe I should give you a reminder of what relative risk is. Relative risk just talks about the odds of something bad happening. In this case, the something bad was coronary heart disease. So relative risk is the risk of coronary heart disease for the treatment group, like those who ate a lot of chocolate, divided by the risk of coronary heart disease for the control group, those who didn't eat a lot of chocolate. So it's like you count how many in the treatment group had coronary heart disease, and that's use that proportion, and you count the proportion in the control group who got coronary heart disease, and then you divide the two. Yeah, so that 0.88 is not a probability. It's not saying if you eat a lot of chocolate, then you have an 88% chance of getting coronary heart disease. It says that those who ate a lot of chocolate, their chance of getting heart disease was 88% of those who didn't. Okay, so reading the chat here, this means the treatment group has a lower risk. Those who ate a lot of chocolate had a lower risk than those who didn't. Okay, so from the 0.88, that would suggest the people who had a lot of chocolate had a lower risk. Maybe eating chocolate is good for you. Now, someone want to interpret from me that confidence interval 0.77 to 1.01. What should I take away from that? It contains 1. Why is 1 special here? The null is 1. In other words, a plausible belief might be maybe chocolate has no effect on your health. If so, that would lead to a relative risk of 1, meaning the risk is the same no matter how much chocolate you ate. You'll notice that this confidence interval contains 1. So, is it possible that chocolate has no effect on your risk of heart disease? Yeah. This is not, another way of saying it is, this finding was not statistically significant. In other words, it could all be a coincidence. It could be that chocolate has no effect. And this outcome they observe would be within the range of plausible outcomes, plausible observations that could arise if chocolate has no effect. Okay, so given all of that, how would you summarize this, like for a member of your family? Say they sent you this article. Tell me what the takeaway is. Sponsored by chocolate brands. Chocolate doesn't do much. Do what you normally do. Misleading. Chocolate has no effect on coronary heart disease. Just eat chocolate. Wishful thinking. No reason to demonize or evangelize food. Food's food. Yeah, yeah, I think you're getting the takeaway here. So as we can see, this study, it's not clear whether there's an association between eating chocolate and coronary heart disease. And if there is an association, it's not clear that there's causation. So I agree with everything you said. Probably not worth paying attention to this article. Any number of reasons to believe that this could be meaningless. There's some evidence for the article's claim, but take it with a grain of salt. People are just looking for an excuse to eat chocolate, so they're grasping at whatever straws they can grab. Scientists found that the people that they studied had less heart disease if they ate chocolate, but they still admit that chocolate may actually have no effect anyway. Study does nothing to impact my current chocolate consumption. Chocolate producers are disappointed. Yeah, yeah. Okay, and then we could keep reading and read the next sentences here and see what else is in there. Professor Adhikari, do you want to jump in on that?
Yeah, I mean, I think the authors of the study are being very upfront, and they're providing their no effect confidence interval first. That's for chronic heart disease. But then the next one, I mean, this abstract goes on, right? So while you guys have been chatting, I've been reading the rest of it. But if you look at stroke, and if you look at cardiovascular disease, then, I mean, it's kind of verging pretty close to one, but maybe there's some weak evidence. Who knows?
Mm-hmm. Yeah, maybe
but
it doesn't help.
Yep. It was not randomized controlled. These people, I believe, as I recall, the people who ate a lot of chocolate were the people who ate the equivalent of one Hershey bar a week. But they were not randomized to do that. So I don't know what you can take away, really.
Yeah, we can see some other connections here that look like there is a statistically significant finding. So there may be an association, but then as we've discussed earlier in the class, it's unclear there's any causation happening. So I think it's a nice example because it illustrates how, in this case, the scientists were very clear about what they did and didn't find. And yet when it translated into the newspaper article somehow made it seem like a much bigger deal than maybe with our understanding now, we can appreciate it as. So in any case, the point is that when you see a headline like that, you can go to the article and you can often get a deeper understanding of what's going on. Let's take another example here. Here is a study that was reporting on a statin, a drug that newspaper articles are reporting. The study found that this drug could lower the risk of heart disease. So here's an excerpt from the paper. You can see a whole lot of stuff here. If you take a look down here, you can see a mention to the hazard ratio, 0.75. There's a 95% confidence interval they're reporting. Remember that hazard ratio is another way of saying that that's the relative risk. You see 0.68 to 0.83, p less than 0.001. Anyone want to interpret that for me? Rejecting the null because P is less than the cutoff. Help me out. What does that mean? Null and rejecting the null and the cutoff. That's a little bit jargonish. It's statistically significant. Yep, that's right. They're finding an association that's statistically significant. There's a very high chance the drug actually works. Doesn't look like you could get this result just from random chance. Yeah. What is the null hypothesis? The natural null hypothesis here would be that the drug doesn't work. The drug has no effect. If the drug has no effect, then the hazard ratio or the relative risk would be 1.0. You can see here that they're reporting that in their patients, it was 0.75. What that means is that the rate of people getting, I think it was heart disease, for those who took the drug was 3/4 of those who didn't take the drug. Yeah.
Professor Wagner, could I
please.
jump in? There was a comment in the chat that I'd like to address. That P less than 0.001 got translated, I think, into there's a very high chance that the drug does something. It may be worth looking at what that chance actually is, that P less than 0.001, that P value. It's the same P value that you've known all along. The P value is the chance of what? Okay, of the conclusion being wrong, incorrectly rejecting the null, the p-value, really? Okay, so here we go. The chance of seeing the observed result or something more extreme, very good. Complete the sentence, you're not quite done yet. Getting the result by chance alone. What do you mean by chance alone here? There are two hypotheses, right? There are two competing hypotheses. There's a null and an alternative. That tiny probability that they found is the chance of seeing the observed result or something more extreme, ... under the null hypothesis. Thank you. Assuming that this treatment does nothing, it's the chance that you get the data that you got or something worse. So it's not actually the chance that the treatment does nothing. This is our little review of what these things mean. Sorry, Professor Wagner, for jumping in there.
I'm glad you did. You could think of it as kind of like the surprise factor. If I went into this thinking this drug was ineffective, then here's how surprising this data outcome would be. Be like less than a 1 in 1,000 chance of seeing some outcome like this if it really was ineffective. So to continue believing that it's ineffective, I would have to believe that a coincidence happened, a 1 in 1,000 coincidence happened. So given that choice between either believing a 1 in 1,000 coincidence happened or the drug is actually effective, you could now figure out how to make that choice. For me, I didn't really have wasn't really committed either way. So now I'm gonna, I might decide, I think, I'm guessing the drug's effective. Okay, so does this prove that there is an association or that there's causation? I see some answers saying association and some saying causation. Trick question, my favorite kind of trick question. You're both right. The data that's highlighted here shows there's an association. Is it causation? Well, actually, if you look up at the top, you can see here it talks about a randomized double-blind placebo-controlled trial. In other words, this is a randomized controlled experiment. So in this case, you can also conclude there's causation. Okay, so interpret it now for me in a way that a member of the public could understand. The drug works. This drug is proven to lower the risk of heart attack. Yeah, drug lowers the risk of heart attack. Yeah. If you're like these patients, taking the drugs will lowers your risk of heart problems. Great. Okay, so there's a whole lot happening here in this article, and you might not understand everything about what's going on there, but hopefully this illustrates how you could pick out some pieces and get a little bit of a sense of what the scientists were doing and what they found. All right, here's one more example based on something seen in the news about a study that looked at lending practices and the effect on minority borrowers, and found that that minorities were receiving a mortgage interest rate that was 0.169% higher on average than non-minorities, which might sound really small, but if you think about buying a house in the Bay Area for $1 million, that's more than a $10,000 difference. So fairly significant. So we could go look at this paper, and here you can see the excerpt from the paper. You can see them talking about the mean difference between these categories. That's something I think we can understand. You can see them talking about how the Oaxaca decomposition is linear. What is that? Oh man. Well, this illustrates that there is a lot more yet you can learn about statistics and data analysis that goes way beyond what we could teach you in this class, but you could learn a lot more in following classes. Okay. I thought it might be fun to do a few more examples looking at stuff in the press on COVID. So here are a few examples from the past year. Here was a article from a year ago reporting on the Moderna vaccine being effective. You can see here the newspaper article says more than 94% effective. What does that mean? Well, we can go to, here was the survey paper that reported on these results. And we can try and read this and see what we can take from it. If you look here, one thing you can see is it refers to randomized, double-blind, placebo-controlled clinical trial. All right, so they're doing a randomized controlled experiment, the gold standard, just like we saw in lecture 2. You can say they've got 30,000 participants. They report that the vaccine efficacy was 94.1%. So that's where that 94% from the newspaper article came from. But what does that mean? Well, here, here you have to know a little bit about vaccination and public health to know what that word efficacy means. And it's a little bit of jargon. It basically refers to relative risk. So 94% efficacy means that the relative risk was 6%. In other words, the percentage of folks who got COVID in the treatment group was only 6% of those who got it in the control group. Okay, so what's the interpretation of that 6%? Or that 94%? What does that mean? Yeah, relative risk equals 0.06. Good question. Okay, comments in the chat. You're right. I apologize for my language. This is yeah, COVID is affecting all of us in many ways, and our family members, and people are dying from it, and it's a big deal. Thank you for highlighting that. I hope that you will not find it distressing to look through this subject, and I apologize for treating it so lightly. You're absolutely right. Thank you. Relative risk. Yes, the relative risk is 0.06. Does this mean that if you had the Moderna vaccine, you had a 6% chance of catching COVID? No, it doesn't mean that. It means that the chance of catching COVID for those who had the vaccine was only 6% of the chance for those who didn't have the vaccine in this study. In other words, in this study, of those who got vaccinated, about 20 times fewer of them got COVID than those who didn't get vaccinated. Okay, so that's the relative risk of 0.06. So that sounds like this vaccine is very effective. That's why it gets called efficacy in the vaccine literature. And you can also see here in this abstract, they report the 95% confidence interval for efficacy, 89 to 97%. What does that mean? Is their finding statistically significant? Could it be explained by chance? Yeah, their finding is statistically significant at the 95% confidence level. So if the vaccine had no effect, then the relative risk would be 1, meaning the efficacy would be 0%. Does this confidence interval contain 0? No, not even close to containing 0. So this is definitely a statistically significant finding. And that's right, you can have 95% confidence that the efficacy is between 89 and 97%. Or if you prefer, that the relative risk is between 0.03 and 0.11. Okay, so that's where the newspaper article got this 94% number from. I've heard sometimes people criticize this 94% number because it could make people think that they have only a 6% chance of getting the vaccine, which, as we see, isn't quite right. So how do I interpret the 94%? The way to interpret that is to say that one way to interpret that is subtract from 100%. and you get 6%. And then to say that if you have the vaccine, all else being equal, your chances of getting COVID are only 6% of what they would have been if you didn't have the vaccine. So 6%, that's about roughly, well, if it was 5%, it'd be 1/20th. So it's reducing the risk of getting COVID by a factor of almost 20 for the patients in this study at the time this was done. Did I answer your questions? Any other questions? Where did the 20 come from? If that had been 95% instead of 96%, then the relative risk would have been 0.05. And if you, 0.05 is 1/20th. A relative risk of 0.05 means that those who got the vaccine had a 0.05 times as much risk of getting COVID as those who didn't. In other words, 1/20th the risk of getting COVID as those who didn't have the vaccine. So 20 isn't quite the right number. It's maybe more like, I don't know, 1/18th instead of 1/20th, but I was just rounding. So let's look back at this original newspaper article and see how they did at reporting this. Here's another quote from that newspaper article. Further on down, they explain. They said, those who got in the group that got the vaccine, only 11 cases were seen. In the group that didn't get the vaccine, 185 cases are seen. So you can see something like 18 times as many cases of COVID among those who didn't get the vaccine. Okay, so I would say pretty good job, newspaper article. Here's another more recent result. I don't know if you've heard about the Bangladesh study that was looking at the effectiveness of masks. Very exciting experiment because they did a randomized trial comparing what the effect of using masks versus not using masks are. And they randomly assigned some villages to a public health program to try to increase the use of masks, and the other villages didn't get that. And here you can find a press release from Stanford Medicine from quoting one of the researchers involved in this study. And you can see here the quote that says, we now have evidence from a randomized controlled study trial that mask promotion increases the use of coverings and prevents the spread of COVID-19. Okay, sounds pretty good. Or if you look around, you can find, here's a blog article you can find on the Bangladesh study, where the conclusion this blogger draws is masks don't work. So why are experts hailing the Bangladesh mask study as proof that masks work? Because they're so desperate to point to something to support their belief system. Okay, what's going on here? What the heck? We've now found two different people who are saying, drawing basically opposite conclusions from this one study. What's going on? At this point, it might be hard to figure out what to make of this if you don't have any particular background in data analysis. Because what are your choices? You know, you go on what feels right or feels believable, or who do you trust, or what are others you trust saying? What are the politicians you trust saying? And that could very easily lead us to a world where we divide into two tribes with two different beliefs about the world, because it's so hard to make sense of these studies and know what to make of them. Well, now that you've taken data 8, we can go look at the study itself, the paper that the researchers wrote, to see what they actually found. Here you can see they report it's a randomized trial. It's a cluster randomized trial, which is a little bit of a funny thing that we haven't quite talked about. It's not individuals who are being given masks or not, but it's entire villages. I saw your comment about how is that ethical? Great question. In some villages, they provided a public education campaign to try to convince people to use masks, and in others they didn't. So in some of the villages, they had respected village elders make the case for why you should wear masks. In some villages, they had a special campaign to provide people with masks for free, and in others they didn't. So I can't tell you about what would be ethical or not, but I suspect the researchers would argue that they were targeting the resources they were providing. It's very common in public health work where we have nonprofits to go provide resources, food or medical supplies to a particular community. But then it's hard to know what the effectiveness is. And so they did something remarkable and really impressive and amazing, which is that rather than providing those resources to entire region, they chose where the resources would go based on this randomization so that we could draw some conclusions about what the effectiveness of these interventions is or isn't. Okay, what else can we see in their paper, their summary of their results? We can see they talked about randomization. We can see they talked about both rate of wearing masks and also symptomatic seroprevalence. Okay, you got to know a little bit about the application domain to know what that means. But that refers to, roughly speaking, the rate of COVID in these villages. And you can see here they talk about adjusted prevalence ratio. What's that? You got to go dig into the paper, but you'll learn that's basically a relative risk. That's the rate of COVID in the treatment group divided by the rate of COVID in the control group. The treatment group received this intervention, the control group didn't. You can see they mentioned this relative risk of 0.91. What does that mean? It's less than 1. What's the interpretation of the fact that it's less than 1? Yeah, the public health intervention, the program to wear masks and encourage villages to wear masks, reduce the rate of COVID, reduce the risk. The confidence interval they report here, 0.82 and 1.00. What's the interpretation of that? Yeah, the confidence interval contains 1. So it's not quite statistically significant. And then you can see they go on to report this for the relative risk for those who are adults who are 60 years and older. And you can see there was a bigger reduction in risk, and that confidence interval does not include 1. So help me out now. If you're going to be charitable to the blogger who says masks don't work, tell me why someone might form that conclusion after reading this study. I hope you could see how someone might form that conclusion. For instance, here you could see how their main result wasn't statistically significant. It's possible you could say that the relative risk reduction was relatively small compared to vaccination. Likewise, if you're a researcher who's saying that this proves they worked, I hope you can see why someone might form that conclusion from this study. This was a randomized controlled study. It was the gold standard in methodology. There appears to be a modest reduction in risk. It's not a ton, but it's not 0. And there There's also statistically significant association for those who are older, and because it's randomized, we can conclude causation. So after looking at this study, I hope maybe it can give you a little bit more sympathy for both sides and help you understand where these folks are coming from, and maybe form your own opinions in an informed base on the data. Okay, so what I've shown you here is, hopefully this gives you a sense of how all these techniques that we've shown you help you interpret studies that you might read in the literature, and also hopefully has helped teach you not just how to read other people's studies, but how to answer your own questions. If you have a question about the world, I wonder if jelly beans are good for my health, that if you have the right data set, that you now have the tools to go analyze and gain some answers on that. Thanks so much for coming to lecture today. I encourage you to come on Wednesday, where we'll have a guest lecture on bias and algorithms. See you on Wednesday.